Okay, hopefully this won't get cut off, but this is the last section for chapter 7, and it's called Bayes' theorem. And so this is a lot of words here, but I think it's helpful to look at an example problem here to see what this is coming from. So it says, again, very similar to one that we've done. Suppose 3 machines, A, B, and C, produce similar engine components. Machine A produces 45%, machine B produces 30%, machine C produces 25%. 6% of the components by machine A do not meet the established specifications. For machine B and C, it's 4% and 3%. It says one component is selected at random from the total output and it's already found to be defective. What's the probability that that component was selected from machine A? And so the difference between the one that we did already and this one is that we already know that we pulled one that's defective. So now we just want to know what's the chance that it's from machine A. And so we want the probability that it's from machine A, knowing that it's already defective. And so one way to think about this is that on the top, we'd have to take the probability from machine A times the probability that it's defective from machine A, given that it's from machine A, over the probability of all the defective ones together. And so the way that we write this is the probability of A given the probability of defective from A plus the probability of B times the probability of defective from B plus the probability of C times the probability of defective from C. Here's the honest truth. I would never write it that way. I would think about it in terms of words. And so if you're like, that makes no sense to me this makes better sense. And I know it's kind of small. Let's see if I can make this bigger and maybe not cut off. Come on, work with me here. So what we're trying to find, the product of the probabilities along branch A through D, right? We want it defective from A. And so if you make our little tree diagram here with A, B, and C, and then defective and not defective from each one, then the top is we want it defective from A. So that's what it means for the top. And then the bottom, we want the sum of the products of the probabilities along each branch terminating at D. So we want all the defective ones, which means that on the bottom, we're going to have to multiply all those together and then add them up. And so either way we get here, gosh, I'm struggling. Why won't it just work? Goodness gracious. Oh yeah, here we go. So on the top we get defective from A, 45% are from A, 6% are defective. So that's defective from A on the bottom, plus defective from B on the bottom, plus defective from C. So either way we get the same answer no matter what you think of it. This idea right here is called Bayes' theorem. When I first looked at it, I was like a little overwhelmed because it looked like so much stuff. But it's basically just taking the probability of what you want on the top over the sum of the ones on the bottom. And so your book says that this is a special case. And again, I'm going to try to make this a little bit bigger since I've zoomed out so that maybe it's not cutting off the stuff. And so this is the book thing from Bayes' theorem. Again, I think making the tree diagram is easier and just thinking about it in terms of words. But it's saying that given some situation that you want it to happen, you have to add up the options on the bottom. And there's a lot of letters there, but just know that's the idea of Bayes' theorem. So let's see if we can do at least one example here. I have 2 examples here, but we'll see how long my video is. So it says, same kind of question here. It says the panels for a 32-inch widescreen CD or TV, LCD TV are located from plants A, B, and C. We actually did one like this already. It says compare with example 6 on page 436. So again, we have percentages that produced from each plant, and then we have 1% are defective from plant A and 2% from B and C. It says if a TV is selected at random and it's found to be defective, what's the probability that it was manufactured in plant C? So I'm really trying to find the probability that it's from plant C given that we know it's defective. So on the top, I'm going to do defective from plant C over adding up all the defective probabilities, right? That's how I'm going to write it. I'm going to make my tree diagram again because to me, that's way easier than thinking about writing out all those given probabilities. That we have plants A, B, and C. And remember that 50% were produced from plant A, 30% from plant C, and 20% from plant C. And then each one we have defective and not defective. And honestly, since we're only talking about defective here, we don't even have to fill in the not defective. But if 1% are defective from plant A, remember that would mean 99% aren't. And the other two are 2%. So defective from plant C would be from plant C and defective. So that would be 0.2 times 0.02. And on the bottom, I'm going to have to do all the defectives. So that's 0.5 times 0.01 plus 0.3 times 0.02 plus 0.2 times 0.02 because we know already that it was a defective one. And then you just use your calculator, and it's 0.27, or that would be 27% chance. So again, the difference between what we did in 7.6 and what we're doing now is we know already that it's defective. Like given that we pulled a defective one already. And I kind of skipped over this part because it was kind of blurry, but your book talks about these crazy words. It says to answer this question, we're talking about the probability after the outcome's already been observed. This is called a posteriori probability as contrast to an a priori, what? I don't even know. Those are weird words. Okay. This one's really blurry too. The theme of the day, blurry video. We can start this one and then we'll finish it in class. But it says income distributions. A study was conducted in a large metropolis area to determine the annual incomes of married couples in which the husbands were sole providers of the house, and of those in which the husbands and wives were both employed. Table 9 gives the results. So this is the income, annual income in dollars. This is what percent of them were married. So like notice $150,000 and over, only 4% of those people were married. And then of the married couples, this is what percent both people worked outside the home. Okay? That's a lot. That's a lot of information. So look at part A. It says, what is the probability that a couple selected at random from this area has 2 incomes? So think about this. We only want the married couples in this. So of the married couples, so of all of these, I want to know what percent of them are married. And so I don't know if you want to make the tree diagram or not, or if you want to just work it out. The tree diagram on this one's going to be really crazy because we have 1, 2, 3, 4, 5, 6 different things. I did make one. A, B, C, D, E, F is what I called it. And then what percent of those are married was my first category, and then whether they both worked. And so I didn't know what to call this. I called it spouse and spouse complement. And so think about on this, the book was really smart, and they made like flat lines here for each one, like A, B, C, D, E, F. A, B, C, D, E, F. So since all of these questions are talking about couples, they're all talking about the percent that are married already. So I did like 4%, 10%, 21%, 24%, 30%, and 11%. And then each one was married, has a spouse, or spouse complement. I kind of like that. Instead of saying single, people can just say their spouse complement, right? Only I'm running out of room. I hope you did better than I did making this. Right? This is a mess. But this one, like 65% are married, so that means 35% are not married. This one, 73% are married, so that makes 27% that are not married, right? Like that's where I would fill that in. I'm going to let you fill it in. But look at part A. It says, what is the probability that a couple selected at random, so it has to be a couple, has 2 incomes? So this has to be 2 incomes. So I think we just have to multiply and add all those up, right? Like 0.04 times 0.65 plus 0.10 times 0.73 plus, I'm going to go down here, 0.21 times 0.68 plus 0.24 times 0.63 plus 0.3 times 0.43 and 0.11 times 0.28. And if you add all that up on your calculator, you get 0.5528, which is the amount of people that are married that both spouses work. Now, B and C, we're talking about a couple that has 2 incomes. So I think this is going to be our bottom number on B and C. I want you to see what you can set up, and then we'll start here in class and maybe look at the diagram they drew in the book, which is much better than my diagram.